Hello and welcome to this course on OPC UA. My name is Siddharth and I look forward to help you quick start your Industry 4.0 journey with a practical introduction to OPC UA. So how does OPC UA fit into Industry 4.0? Let's answer that with an introduction to RAMI 4.0, which is the reference architecture model that was developed to modernize manufacturing in Industry 4.0. RAMI 4.0 is a three-dimensional reference model that helps all stakeholders to have a common understanding of the life cycle of products, factories, machines, or orders together with the hierarchical levels in a manufacturing environment. RAMI 4.0 outlines a service-oriented architecture, abbreviated as SOA, in which assets in the manufacturing environment are networked and can expose services in a vendor and technology-independent manner to other assets or to higher-layer IT systems. This brings us to OPC UA, which has been recommended as the standard for implementing the information modeling and communication layers in this reference architecture. Looking at it from an OSI layer perspective, OPC UA will be at the application, presentation, and session layers and will leverage TCP/UDP transport over a variety of wired and wireless networks. At this point, you might be thinking about how to get started with information modeling and how much effort it would take to create information models for your device or machine. Having an idea of companion specifications is a good place to start answering such questions. Companion specifications are information models that make it easier to achieve interoperability between equipment from different vendors. Let's take a look at some scenarios that can help you visualize the benefits of companion information models. One scenario is in the plastics and rubber processing industry, where robots and machines from different vendors are expected to operate together seamlessly. This can involve operations such as an injection molding machine making a part and a robot removing that part from the machine. Irrespective of which machine or robot vendors are involved, operations such as removing a part from the machine are common and can be standardized across vendors. This reduces the efforts to configure and operate equipment from different vendors, thereby reducing integration costs for the end users of such equipment. Another scenario is in a product distribution warehouse where RFID or barcode readers from different vendors have to be easily integrated into the IT system of a logistics company. Though the read range or capabilities may be specific to readers from different vendors, there are a number of common functions related to configuring and reading data from them. Creating an industry-specific standard through a companion information model greatly reduces duplication of effort to integrate these equipment together as part of a larger process. As you can see, a number of companion specifications have already been created for industries such as CNC machine tools, plastics and rubber processing machinery, packaging machinery, oil and gas, industrial kitchen equipment, etc., among others. If your device or machine is a part of these industries, you may be able to save yourself a lot of effort by leveraging the companion specifications that have already been created. This brings us to the question, why would competing vendors in an industry join together to create companion specifications? This is driven by the interoperability requirements specified by their customers, that is, end users who wish to simplify the integration of devices and machines from multiple vendors into their manufacturing processes. The vendors who are unable to meet such interoperability requirements in a standard manner will find it increasingly difficult to sell to such end users. At the same time, we cannot forget the huge base of legacy devices and machines that are already installed since the last 20 to 30 years in factories around the world. These legacy equipment will also need to be integrated as part of larger industrial IoT use cases. Many of these equipment will be using legacy communication protocols such as Modbus, CAN-Open, Profibus, DeviceNet, etc. on top of physical layers such as RS-422 or 485. More recent installations in the last decade will be using Ethernet-based protocols such as Ethernet IP, Profinet, Circos, PowerLink, and EtherCAT, and they will also need related companion specifications which are under various stages of development. This can bring up another question. Why take the effort to create information models and implement OPC UA instead of continuing to use the legacy protocols? As mentioned before, the integration of devices and machines from multiple vendors needs to be simplified for end users. For integration to be simplified, the devices and machines need a standard mechanism to query each other's capabilities, configure themselves, and interact with each other to interoperate according to the required manufacturing processes. Such mechanisms are not possible with the legacy protocols that use less flexible concepts such as register memory maps, object dictionaries, and device description files. The interoperability challenge also led to the creation of OPC and its evolution to OPC UA as we know it today. The OPC standard was first released in 1996 with the aim to provide a standardized communications layer between human-machine interface or supervisory control and data acquisition systems and programmable logic controllers or PLCs. This requirement came up since PLCs used different protocols such as Modbus, Profibus, etc. as mentioned earlier, and there was a need to provide a generic interface for exchanging information irrespective of the underlying protocol that was used. OPC was abbreviated as Object Linking and Embedding (OLE) for process control. Today, it is known as OPC Classic and has seen adoption across industries such as manufacturing, oil and gas, and building automation over the years. However, it is restricted to the Windows operating system and is not flexible enough to meet the requirements of service-oriented architectures that are now being introduced to modernize manufacturing systems. In response to this challenge, in 2004, the OPC Foundation developed the Open Platform Communications Unified Architecture (OPC UA) specifications that build on top of OPC Classic and provide a more secure, platform-independent, and service-oriented architecture that is scalable across a wide range of compute hardware and operating systems. OPC UA is also extensible, and this makes it future-proof by enabling updates to leverage newer security standards and transport protocols, among other features. With the service-oriented architecture of OPC UA, you can browse the information model of a device, read and write current and historical data, execute methods and receive notifications for data changes and events through the client-server communication model. In this model, a server receives requests from a client and sends the results back to the client along with the response. Though the OPC UA client-server communication model is feature-rich, it is not feasible for some scenarios such as high-frequency data and event notifications between large number of sending and receiving devices such as sensors, actuators, and PLCs, which are also power and latency constrained. This led to the OPC Foundation releasing the PubSub extension as Part 14 of the OPC UA specifications in 2018 with an alternative mechanism for data and event notification. PubSub has been optimized for one-to-many and many-to-many configurations, in contrast to the connection-based guaranteed delivery between each client and server in the client-server model. Instead of requests and responses, publishers send messages to a message-oriented middleware and are not aware of subscribers. Similarly, subscribers register with the middleware to receive messages that they are interested in, and subscribers are also not aware of the publishers. OPC UA PubSub can also be used to extend the application of OPC UA technology to highly scalable cloud applications in which a large number of sensors can send data securely to the cloud through broker-based infrastructure by using popular transport options like MQTT and AMQP. In addition to enabling low-latency communications, OPC UA PubSub is also positioned to leverage future technologies such as time-sensitive networking, TSN, to deliver real-time guarantees. OPC UA PubSub over TSN can be used as a real-time communications protocol between sensors, actuators, and PLCs at the field level. This is especially important for time-critical applications such as motion control in machines, which demand sub-millisecond cycle times with sub-microsecond jitter performance. The growing interest in OPC UA PubSub over TSN led to the creation of the Field Level Communications FLC initiative that was started in November 2018 within the OPC Foundation. This initiative aims to enable vendor-independent interoperability right from the sensors, actuators, and controllers in the field layer and up to the cloud for all relevant industrial automation use cases. The goal of this initiative is to deliver an open standards-based approach to implement OPC UA over TSN and associated application profiles like I/O, motion control, safety, and system redundancy. This initiative also integrates well with existing joint working groups engaged in development of ongoing companion specifications related to machine applications. You now have an introduction to OPC UA in Industry 4.0, the benefit of companion specifications, and evolution of OPC Classic to OPC UA. You've also seen an overview of the OPC UA PubSub extension and future direction with time-sensitive networking and the field-level communications initiative. Let's take a look at the topics that will be covered in the rest of this course and how they have been structured as practical examples. You'll start by creating an information model of a custom object type that includes variables that are commonly exchanged between an OPC UA server in a machine and an OPC UA client in a human-machine interface or HMI. Then you will learn how to use the open source OPC UA stack Open 62501 to build examples for data access services such as read, write, and subscriptions. Following this, you will learn how to implement method calls before moving on to enabling security features. After this, you will learn how to create and monitor events and then alarms and conditions. In the final topic, you will learn how to buffer and access historical data. Once you've completed these topics, you should be well on your way to implement the most commonly used OPC UA features in your own applications.